Thank you for joining this webinar from the Engineering Integrity Society. I will now hand you over to today's host, Martin Bache, for an introduction to today's presentation.
Thank you, Sarah, for all the work that you've put in to organise today's webinar. It's one of a series that have been organised over the past months since we've been under COVID restrictions. Obviously, today we're pressing ahead with the Teams format. Welcome to everybody who has dialed in. We'll just, while we wait for any late people who want to join, just a little bit of background about the Society. You should all be able to see a slide there. This describes the divisions of the different technical groups who meet on a regular basis for the Engineering Integrity Society. The Society is a charitable institution for the understanding and dissemination of various engineering topics. 4 subcommittees meet roughly on a quarterly basis. We have a simulation, test and measurement group, the durability and fatigue group, that's the group that I am most closely affiliated to, the sound, vibration and product perception group, and then finally a specific team of young engineers who get together on a regular basis. The Society organise various strands of support for engineering, in particular supporting young engineers at the beginning of their careers, whether that be in industry or in academia. And as I say, there are a regular set of webinars, seminars, and some face-to-face events that are still in the planning. So I would encourage everyone to look out for future events. And if you're not already a member, perhaps I can encourage you to become a member and get involved in one of these organising groups that you can see on screen at the moment. I believe there's another slide that Sarah can show us with some up-and-coming events. Here we are. We're currently running a photography competition. Anyone with any interesting images from their research or teaching activities, please think of putting an entry into the photography competition. Closing date is now 31st of December of 2021. The webinar series, the next event after today will be around renewable energy and storage, and there's a talk there detailed for the 15th of December. And then in future there'll be another webinar on strain gauges, principles and applications. That's after Christmas into the new year on the 19th of January. Every year the Society organises an exhibition. Traditionally that's held at Silverstone race circuit, and that is a very important event for the Society, very well attended, and I think anyone who's interested in that should make every effort to get along to that. So that's scheduled next for May of 2022. Obviously that's all dependent on COVID restrictions at the time. And as I say, the Young Engineers Forum, they have meetings at various dates throughout the year. Any information regarding any of these events, webinars, seminars, etc., you can go to the EIS website, or there's some contact details there that can get you directly to Sarah, and she can help you with any of those events. So on to today's webinar. On behalf of the Society, I'm very pleased to welcome Neil Glover, who is the Head of Materials Research at Rolls-Royce, based in Derby. He's both a Fellow and the current President of the Institute of Materials, Minerals and Mining. Neil has over 25 years of experience of materials engineering for aerospace and other high integrity applications. His current role is focused on materials technology to support new product opportunities in Rolls-Royce, including electric and hybrid flight. Previous roles have spanned multiple business sectors and materials engineering in general across the product life cycle. For many years, Neil was responsible for Rolls-Royce's aerospace materials research portfolio, and in particular, the links between the company and its extensive external network for materials research. And that's where I've become friends with Neil over many years, probably going back certainly into the 1990s, if not before. Neil's a bit younger than I am, but there we go. Neil's a regular speaker at national and international events, and he has been a member of numerous national advisory groups in these material technologies. He's a strong advocate of STEM education, and he's a regular speaker at schools events, certainly within the Derby community. So the title of his talk today will be Materials Challenges for Sustainable Aerospace. And with that, we'll give Neil control of the Teams meeting. So thank you, Neil.
Thank you, Martin. Hopefully you can hear me fine. Yep. Okay. I'll put my slides on to share. Okay. So if you give me the thumbs up, can you see the slides okay? Excellent. I'll start then. So thank you for the introduction, Martin. I am, as you say, Neil Glover. I'm Head of Materials Research at Rolls-Royce, and I look after all things materials technology that have the potential to offer promise to the future of our business, particularly beyond the sort of traditional gas turbine and aerospace materials. And I was going to talk to you today about the challenges of sustainable aerospace and what that means in terms of materials for hybrid aerospace or alternative fuels from the point of view of materials performance and durability. Before I go into that, Martin has already said I am the current president of IOM3, so I'll give a shameless plug for the Institute. If you are a member, or if you're not a member, if you go to the Institute website, there's lots of information and material there, particularly around sustainability, particularly associated with the Sustainable Futures Week that the Institute did in the run-up to COP26. There's quite a lot of webinars and podcast materials and so on that people can look at if they're interested in material sustainability more generally across the life cycle. Okay, so what I'll talk to you about for the next maybe 40 minutes or so. Very short introduction to Rolls-Royce. I talk a little bit about sustainable aerospace and what it means. Hybrid aerospace in particular, and the different kinds of hybrid system, the different configurations, and what that actually then means in terms of the different elements of the system that materials need to be supplied for. I'll then talk about some of the materials technology challenges associated with hybrid aerospace across the kind of range of materials that are in there. And I'll talk a little bit about hydrogen as an alternate fuel. So who are Rolls-Royce? Many of you will know about Rolls-Royce. You'll probably know about us in the context of aerospace, civil or defence aerospace. We are one of the world's leading industrial technology companies. We're active, as we say, in civil and defence aerospace, but also in power systems for use on land and at sea, and in the nuclear sector. And our purpose is to deliver power systems that will meet the future needs of society. And we do believe that technology has the power to deliver cleaner and more sustainable power systems, and that's vital for the future needs. And we believe that we are very well positioned to meet those requirements across all of our sectors. And we are committed to the transition to a low carbon economy. It's clearly a global imperative, and it's also a business imperative for companies like ourselves. And we are very much committed to playing a leading role in that transition to decarbonisation and to reaching net zero in the sectors in which we operate by 2050. And I'll talk more about that. You can find out a lot more about that on the Rolls-Royce website and what those commitments and roadmaps are. So Rolls-Royce has always been a pioneering company in terms of innovation, from the early days of flight at the top left, with that's probably an Eagle engine on that, through the dawn of the jet age, supersonic flight, vertical takeoff landing systems, through to modern combat and defence aerospace applications. But the world continues to change, and the challenges continue to come in. And material science has always been at the forefront of that challenge. And I always like to just stress with this slide that everything we do is about materials science, but it's also about materials engineering. So we will be designing materials, understanding materials at the atomic level, designing and developing alloys, looking at micromechanisms of deformation and structural integrity and lifing. But we need to be able to translate that through meaningful manufacturing at scale into real world components, and we need to be able to do that in a reproducible way, and a way which is cost effective and achieves the necessary production rates. And then we need to assure ourselves that that product will continue to behave in a reliable way throughout its service life. So it's a sort of fusion of materials science and materials engineering in everything we do. And if things can't be translated through into meaningful product, then it's that's a barrier for us in terms of the implementation of any technology. We also address things across a full range of size scales, time scales, cycle scales, and temperatures within our products. This is a chart that was much beloved of one of my colleagues, Dave Rugg, who Martin knows well. So we deal with things that are over a time scale of many years or decades in terms of creep mechanisms of long time deformation of components. Our systems will be in service for many, many years, right the way through to things that happen almost instantaneously in fractions of a second, if we're thinking of impact events or containment or processing techniques like laser shock peening. And then similarly, we have single cycle events there with impact and overload, and we have things that are through the low cycle fatigue regime and into the many cycle, high cycle fatigue domain of vibrational loading and aerodynamic forcing. We've got applications that span the front face of the engine where it's exposed to cold air at altitude, which could be minus 50 or below, through to the combustion chamber of the engine where things could be at well over 1,000 degrees centigrade. And therefore we have a full range of materials from polymerics through to light alloys, high temperature alloys, coatings and ceramics. And we have to understand them at the full size range, as I've said, from the sort of atomic nanometer size scale up to the full size of components and some of the larger microstructural features that are in there. So there's a real breadth of challenges and technical issues to be addressed. And that is true of all the materials we conventionally address, the structural alloys and the light alloys, the composites. It's equally true of all of the materials that I'll talk about in terms of electrically active materials for hybrid propulsion. We need to still have that full depth of understanding from the underpinning science through to the engineering. And that foreknowledge of exactly how these systems behave in service, so that if we start to see problems, we already can think our way through to the solutions, and we're not trying to generate that detailed scientific understanding in the face of an issue. You need to be forearmed with the knowledge and expertise. We obviously have a whole range of tools and techniques that we can deploy to that, more so than ever. One of the challenges of material science, I think, at the moment is that there are so many techniques that you can deploy to understand the behavior of materials, and knowing which is the right technique to use, and knowing how to describe and capture the wealth of information that comes back from the technique and turn that into a usable design process is often the challenge. But we have to look at things at the microstructural scale, we translate that into fundamental mechanisms of strengthening or deformation, and then be able to make component level predictions of strain distribution, load, damage accumulation, and so on. So that sort of sets the scene in terms of material science, I guess, and the way perhaps we think about it. Aerospace decarbonisation. This is the Trent XWB. It's currently the world's most efficient gas turbine. It's obviously a fairly conventional product, but we know that that's not enough. We know that we have to make our products more and more environmentally friendly. and that we have to increase the sustainability and particularly decarbonise. So there are three sort of fronts by which we can decarbonise our portfolio. We can look to further reduce fuel consumption, which automatically reduces emissions, and while also looking to improve other environmental attributes like noise. We also develop entirely new low carbon technologies and capabilities across our business. So we're looking where we can use our knowledge to enter into new markets or business sectors. So you may have heard about things like small modular reactors. That could be an example of that. Work that we're doing on things like microgrids, where we can use our engineering expertise and systems expertise to bring new sustainable technologies to market. And then delivering in our own internal operations and facilities and back through our supply chain. We know that the environmental impact of that product is predominantly through its long service life. That's hardly surprising when you talk about a jet engine. So we very, very much need to focus on in-service product performance. But that doesn't mean that the embedded carbon in the product when it leaves the factory gate is not important. So we need to continue to address that carbon footprint in our domestic facilities and that upstream carbon footprint from our materials, whether it's the mining, the refining, the processing, and the primary forging or machining that takes place ahead of when it comes into a Rolls-Royce facility. We have targets for CO2 reduction, for NOx emissions and for noise. Now we can see where our current engines sit on those targets. We can see where our next generation engine UltraFan would sit. And we know that we have to continue to drive that performance forward in line with these targets and with our net zero commitments. And that's essential for us to remain in business, and it's essential for the future of all of us. And that's where hybrid aerospace comes in, looking at more radical ways in which we can reduce the impact of our product. So how can civil aerospace continue to reduce environmental impact and drive innovation? And this would be equally true in other sectors of aerospace, but we'll just take civil as the example. Well, we can continue to optimize the gas turbine, and UltraFan is an example of that. But it's equally important that stress as we go to electrification. This isn't a kind of and/or scenario. Many of the electrified products are hybrid products. So there's some form of prime energy generator in there, which in many cases will be a gas turbine. I guess analogous to a hybrid car. So it's equally important that that gas turbine is running efficiently. The gas turbines of the future may well be running on a sustainable aviation fuel or an alternative fuel such as hydrogen, but that fuel will come at a cost, and a cost in terms of energy to produce it, as well as a kind of commercial cost. And so it will be important that we burn as little of that fuel as possible for the whole efficiency of the system. So continuing to optimize that gas turbine so that it is more and more and more efficient as part of that whole system remains important, and it's just kind of it's really important to stress that point, I think. And then there'll be closer and closer integration between airframe and engine to get the whole system benefit and the electrification angle of bringing electrification into the propulsion chain. So just on the first, the sort of more traditional view of that, if we look at the gas turbine materials technologies that we might be more familiar with, and where are they going? Well, if we look at the cross section here of an engine like UltraFan, we are interested predominantly in two things: taking out weight and increasing cycle efficiency, so through increasing rotational speed, core pressure or core temperature. So lightweight composites for the fan system, organic matrix composites for as much of this as possible. So the blades, the statics, the casings and so on, the spinners. Increased performance light alloys potentially as part of that containment system. So we might think that titanium alloys are 60, 70 years old, even older than me and Martin, but there are still advances to be made there. There are still new alloys being developed, and we're active in that area with our supply chain. Back through the core of the engine, then there's always a drive for higher temperature materials to increase the cycle efficiency, whether that's in the turbine or in the compressor. and the associated joining technologies that go along with that. These things never get easier to weld or join. And the coatings and sealing technologies required to efficiently seal the gas path or to protect the metallics from the temperatures and aggressive elements present in the gas stream. And then lightweight LP turbine and exhaust structures. We see ceramic composites coming in. We see additive layer manufacturing coming in to enable complex geometries for complex cooling. And I think there I would stress that for me, additive is a technology which is all about geometric freedom. Sometimes we discuss it in the context of material yield improvement or cost. I don't think that's at all the primary driver. The primary driver is geometric freedom for the designer. And critically for UltraFan, we see the introduction of high power transmissions. So this is a gearbox that sits between the core of the engine and the fan system. So there's a requirement for very high performance transmission steels. And then we look at alternative fuels. So those alternative fuels could be a synthetic aviation fuel, a green aviation fuel produced from, well, any number of processes or feedstocks that do need to be carefully considered for their own sustainability. Ultimately, potentially from directly from power. So a fully synthetic fuel from derived from green electricity and water and carbon dioxide capture. And also potentially hydrogen for use in as part of an aerospace system, which could be a combustion engine or it could be a fuel cell. Another little plug here, there's quite a lot of stuff about the hydrogen economy that you can find online, particularly through the Institute of Materials, Minerals and Mining, I should say. Okay, so Martin will be very familiar with this. Some of you on the line might be, but perhaps the one of the ultimate tests around materials technology is the high temperature turbine discs. And there we really are extending the limits of conventional materials capability with nickel superalloys and extending what's possible in terms of a combination of property requirements, overspeed, low cycle fatigue, defect tolerance, dwell crack growth behavior, thermomechanical fatigue in some of the rim features, and environmental stability, as well as microstructural stability. And it's an integration then of the materials chemistry development, the processing, which is typically a powder route, the conversion, the forging, and the joining, which you see across the bottom, and then the life validation. The reason part of the reason I put that there is that range of challenges in terms of environmental stability, mechanical and cyclic stability, and thermomechanical performance could equally well apply, as we'll see, to some of the rotating and mechanically loaded parts of a hybrid, a motor generator system for a hybrid aerospace propulsion system. So the sort of challenges and the fundamentals of material science remain the same, although the system that we're engineering around or the materials might be different. But the kind of issues that you have to consider, the broad issues of integrity, remain sort of consistent as a theme. Similarly for ceramic matrix composites, whether it's silicon carbide systems for the replacing nickel-based superalloys in the hot parts of the turbine, or whether it's oxide-oxide systems for introduction as lightweight structures towards the rear of an engine. It's the same kind of issues. How does the system fundamentally behave? How do you manufacture it consistently? How do you capture its behavior at a microstructural level and a macroscopic component level? How do you understand that? How do you deal with thermomechanical loading and environmental challenges? And those are things that we're sort of very actively progressing as technologies. But they're also understandings, again, that read across into hybrid systems, particularly where we might have ceramic components in hybrid systems, although the ceramic system itself might be different. The challenges kind of read across. So, electrification. Electrification's not something which is new to Rolls-Royce. Through our Power Systems group out in Germany, RRPS, we make hybrid systems for trains, and we have in the past been involved in hybrid systems for marine. So that's the integration in all cases of some sort of energy storage, the control and power electronics, and the motors and generators and drive systems. So that systems understanding is there and can be translated into aerospace. How does a hybrid impact aerospace, or there are a number of different sort of embodiments of electrification into aerospace. The embodiment might be incremental, a sort of more electric approach, a greater generation of electrical power from the system, and then a greater supply of electrical power into the airframe. So just sort of a generally increasing content of electrical load into the system. Or it may be more disruptive, where we see that electrical power being a fundamental part of the propulsion chain, with electrical propulsors introduced onto the structure of the aircraft. And that may then enable new airframe concepts. If you're going to have electrical propulsors, you can put them in different locations. You can take the power to them electrically, perhaps more easily than you could have located a large gas turbine. So you can achieve different geometries. And that may mean that the scope of supply may change, and we'll see new entrants coming into the market in terms of airframers, particularly in some sectors, the smaller aircraft sectors perhaps. So there's a number of different systems which it probably makes sense to try and get your head around a little bit. So schematically, if we start at the left, at the smaller end of the sort of the size range, the power range, or the aircraft range, we might have an all-electric system. So this might be for you see them for the light leisure aircraft or trainer market perhaps, or it might be some of the things that are proposed for sort of urban air mobility, sort of air taxi type things, where you have an energy storage system, a battery system, you've got controlling power electronics, and then you have a number of electrical motors and propulsors located around the airframe. So the kind of multi-copter concepts and so on, which can give you the vertical and horizontal flight capability, and can also give you a degree of redundancy in the propulsion system. You can then have hybrid systems, and that hybrid system can be configured in a number of ways. I won't talk about turboelectric, that's a bit niche, where the gas turbine just drives direct through a generator. But if we look at series hybrids, this is where we've got a battery system which can power a number of propulsors, but we've also got a gas turbine or another prime mover which is able to generate through a generator the electrical power to charge the battery or directly power the propulsors. So this is quite analogous to my sort of plug-in hybrid car, where you've got the gas turbine as a prime mover in certain parts of the flight cycle, or a range extender. And then we've got parallel hybrid systems where the gas turbines are producing thrust in their own right, but they're also powering motor generators which are working with power electronics to charge a battery system and potentially drive additional electrical propulsors which can be located around the airframe. So that can enable you to provide extra thrust electrically at certain parts of the flight cycle. It can enable you to manipulate the cycle of the gas turbine to flatten out peaks for takeoff and landing. And it can potentially enable you to distribute additional propulsors in different locations around the airframe to get aerodynamic efficiencies. So it's quite powerful in terms of the number of different optimization tunes you can play with the system, and the number of different ways you can sort of use your electrical knowledge in distribution and power generation and propulsors. And they play into different markets. So I said the small end of the market, probably the personal air mobility, is probably all electric, veering into hybrid. And then as we get larger and go through the regional into the narrow bodies, it's probably a hybrid electric model. And here you can see various of the different configurations have been proposed. And then when we get into wide body market, it's probably the more electric with a greater electrical power offtake, or it's some of these might be the parallel hybrid concepts. So it's kind of horses for courses. But whichever way you look at it, there's a potential benefits to be gained in the different market sectors through the introduction of hybrid systems. And just to show that this is real, this is the City Airbus. So this is a demonstrator that colleagues out in Bavaria did in collaboration with Airbus. It's a eVTOL, vertical takeoff and landing system, with 8 propulsors, RRP200D propulsors, back to back. So you can sort of see them here, powering 4 sort of propulsion locations. and that has done a number of demonstration flights. It is a demonstrator. It's not going directly to product, but it shows you that it's real and it's flown, and you can find video clips of it flying on the internet. And equally recently, you might have seen the stuff about us flying our Axel aircraft, which broke the world electric speed record. And there's lots of other things about various of the product development. So this is real, it's happening, and it's coming. In all of these systems, materials technology is central, and power density is critical. So this is looking at the three elements of the system which are common: the motor generator, the power electronics, and the energy storage, and the kind of challenges. So we probably sit somewhere like this. A lithium-ion battery system is probably about 300, 350 watt-hours per kilo, high performance, depending on quite how much of the system you count, the packaging and the cooling and things. A motor generator might be about 8 or 10 kilowatts per kilo, and power electronics similarly. And we need to drive that up. I mean, these are sort of aspirational targets for a future narrow body. You can sort of debate how realistic some of these are, particularly for the energy storage. But these are targets that people are driving towards, and to achieve these, we really need to advance the materials technology. It's no different to gas turbines, that things are limited by materials capability to a greater or lesser degree. So what we're talking about, I don't know how familiar people are with electrical machines. I wasn't that familiar with electrical machines 4 years ago. I'm painfully familiar with electrical machines now. This is a motor generator rather than power electronics or a battery, because it's a little bit easier to discuss, and it's got some interesting performance and durability challenges we can talk about. But essentially, we're talking about permanent magnet machines. So we've got a rotor, which is a soft magnetic stack of laminations with some permanent magnets bonded on the outside, which produce the flux. They're then held in place by some kind of sleeve. This thing spins, and it spins potentially at quite high speed, thousands of RPM, many thousands of RPM, and the magnets have to be held on. So this sleeve goes over the outside, applies a compressive load, keeps everything in place. That then goes inside the rotor, the stator assembly, which is the copper coils, which can have any number of configurations and forms, that are essentially wound around a stator, which is again soft iron stator, which then, if it's operating as a generator, this is spun, the flux rotates within the coils, and the coils produce the voltage. If it's operating as a motor, we excite the coils, and that creates the rotational movement that drives the shaft. It's just kind of an inverse, but essentially the same system. And if we want to increase the power density, then there are only a number of things we can do. We can spin it faster, so the mechanical loads go up on the rotor in particular. We can drive more current through it or increase the voltage, in which case the thermal loadings will go up because we'll put more electrical heat in, and we put a greater challenge on our insulation systems. Or we can increase the magnetic loading, the magnetic flux coming from the magnets going through the soft magnetics, in which case we will be driving to higher saturation densities of the magnetics, and also producing thermal losses, which need to be handled by the thermal system. In practice, we'll do all of those, as we always do. So spin faster, more magnetic loading, more electrical loading. So we think about the materials for that. We need to think about the materials throughout the life cycle. We need to think about developing new materials potentially, although lots of the materials used for electrical systems, the magnets, the soft magnetics, are quite mature systems. We might be using the niche, the best-in-class materials, but they're relatively mature. So it's probably more about understanding materials performance at these limits of the envelope and for long times at temperature and under stress. And I'll come on to how there are some fairly large gaps in knowledge there. It's about controlling manufacture so that it's reproducible and fixed process. It's about understanding quality and integrity and managing service life, and also about repairing, reusing, and recycling. There are some materials in here which are strategic or critical, or technology critical metals, however you like to call it, like cobalt in the soft and permanent magnets, or samarium, or rare earth elements. And it's important that we're able to optimize the efficiency of those, both in the original manufacture and through the recycling. And again, we know that use is the predominant, this is a kind of environmental impact scale. We know that use is the predominant contributor to environmental impact, but it doesn't mean that manufacturing and maintenance are not important. So we need to think about this in a whole life cycle analysis kind of lens. So materials challenges. There's a little machine on the right, a little kind of permanent magnet alternator machine that we might use for auxiliary power. It's not a main motor, but the geometry is the same. So if we think about the key areas of challenge, high voltage insulation, we're going to run these machines at high voltages, hundreds if not kilovolts levels. We're going to operate them in aerospace environments of fluctuating temperatures, elevated temperatures, and at altitude, which all challenges the insulation. I'll come on to that. There's then associated issues of high voltage with cabling and terminations, and the consistency, quality of manufacture, and how that might interact with insulation performance and voltage performance. There's the magnetic materials and their through life performance, and understanding the detail of their performance, as I say, under stress and temperature. And then there are lots of system interactions that we need to think about through life, as well as the issues of sustainable sourcing. That's the Axel aircraft that's recently broken the world electric speed record. It's really, really nice. Lovely aircraft work. Worth a look at some of the videos. So if we come to electrical coils and insulation, there's lots and lots of different configurations of electrical coil. They can be large bars packed into slots. They can be random wound copper filament, or they can be very complex bundles of fine filaments and Litz wire configurations to manage high frequency losses. But in all cases, you've got a kind of copper conductor. You've got usually a first layer of insulation around the strand, some kind of a resin, and then you'll have tape layers and windings of things like Calmica layers, and then you'll have impregnation resins, and then there's slot liners and protective layers that go inside the stator slots, and spacers and things. So lots and lots of non-metallics to provide the insulation performance and to physically locate the coil and to provide the thermal paths. So quite a complicated duty and quite a complicated assembly of components. And particularly in our systems, it's operating at relatively high temperatures for these polymeric systems, perhaps well over 100 degrees C, approaching 200 degrees C. It's operating at altitude, which, if you know anything about electrical discharge, there's something called Pasching's minima, which is where at altitude you get a lower voltage for discharge. So we need to manage that in terms of the threat to insulation. It may be directly cooled by a dielectric fluid, so we need to manage the issues of fluid compatibility and through life aging. And we need to manage the issues of manufacturing reproducibility of all this stuff, as well as looking to the future. And when we look to the future, there's possible to drive for better resins for impregnation, and to add fillers, potentially to get better thermal performance, better transfer of heat to the heat sink, which is the stator. Or we can look at additive technologies for coils to get complex geometry into the coils, for better packing efficiency or better electrical efficiency. When we look at the magnets and the permanent magnet rotors, we've got a rotor hub, which is a back iron cobalt in our case often, or perhaps iron silicon in a low performance machine. We then got the magnets stuck on with an adhesive, which also provides some electrical isolation. And then this thin sleeve that goes around the outside that retains them on in terms of the rotational strength. We see a number of challenges here. The permanent magnet materials, these can be samarium cobalt or neodymium iron boron. They are environmentally sensitive, particularly the neodymium iron boron. They will oxidize or potentially corrode if not adequately protected. And the oxidation, particularly of samarium cobalt, is quite complex. It's crystallographically sensitive. These are crystallographically oriented, so the C-axis is in the pole direction. And they oxidize in this kind of sawtooth way, more rapidly perpendicular to the C-axis and less rapidly on the C-axis faces. You know, this kind of intrusions of oxide and growth of a soft magnetic layer on the outside. So that needs to be understood, along with all the other through-life degradation mechanisms associated with the magnetic loading and the thermal loading and the time at temperature. Similarly for the soft magnetics, they have a lovely magnetic loop at zero stress, But when you start to apply tensile or compressive stress, the loop distorts. And that's both quite difficult to characterize and test, because it's difficult to apply mechanical load and measure the magnetic performance at the same time, particularly in compression. But it's important to understand so we can get the modeling and performance right. And it's also important that we understand all the detailed processing microstructure relationships in these alloys. There's complicated mechanisms of short and long range order, and how that evolves through heat treatment, and how that might evolve through time at temperature. And how these thin laminated structures, which might be made up of thousands of kind of 150, 200 micron laminations, how they behave mechanically in service when subject to high compressive loads from the banding and to cyclic thermal and mechanical loads in operation. So again, lots of complexity to be understood. We also need to understand what we do with the magnets at end of life. They contain neodymium or samarium, which is a critical material. It's expensive. The cobalt is also expensive. It's important that we recover them, but they're often laminated assemblies in their own right, made up of little slices or blocks of magnet that are laminated with adhesives to manage eddy currents, and they're bonded or glued into the whole assembly. So how you recover them, how you break them down, and how you get them back at end of life is a kind of interesting challenge. And this is work that's been done at Birmingham by the Permanent Magnets Group there, Alan Walton, on hydrogen processing to decrepitate the magnet, which basically causes it to revert to powder. And then you can sieve out that powder, screen it, and reprocess it, because it's originally a powder route anyway. So you can recover your valuable elements. It's kind of a neat technique. If we come on to look at the rotor sleeves, the rotor sleeve is retaining these magnets. They might be going around at 10,000, 15,000 RPM at like 180 degrees or something, under very high pre-stress. So this could be metallic, but in high performance machines, it'll probably be a composite. So we need to understand the high temperature performance, relatively high temperature performance of that composite, its behavior under long-term exposure at pre-stress, so thermal, mechanical and viscous behavior, the way it behaves as the rotor is trying to expand and contract under thermal cycling, so a kind of high R ratio fatigue behavior, and exposure to any fluids, as well as the electromagnetic interaction. So are we getting electromagnetic eddy currents excited in the carbon fiber structure, and are we causing local heating? And we've done full-scale spin testing as well as full-scale system demonstration of these composites, and there's a real challenge there for developing novel resins, optimum fiber architectures, and novel mechanisms of toughening to get the best behavior we can from those composite components. And then there are issues of systems performance, and I've just illustrated a few. You can get these kind of bearing current effects, where you get circling currents through the whole structure of the machine, which then cross the bearings into the shaft line of the electrical generator, and then rather than the whole gas turbine, just the electrical generator. And then you can see this kind of erosion of the balls and the bearing races, and this classical fluting behavior, which is very characteristic of bearing currents, and that needs a kind of whole system approach to minimize. We have impact and containment issues always. This is a fan blade test, but we will have on this rotor. You've got to think about containment, were the banding to fail, and you've got to think about potential foreign object damage effects that could happen in these structures. And we need to think about long-term exposure to fluids, whether those fluids are oil-based dielectrics or perhaps some more novel fluorocarbon type dielectrics or water glycol type dielectrics, or other fluids that might be present in the system, anti-icing fluids, salt washing fluids, that kind of thing. And then obviously we need to think about thermal management, heat extraction, heat exchange, and fire protection, particularly if we're thinking about battery systems. Perhaps there's a big challenge of thermal management, cooling, heat extraction, and management of the threat of fire. Okay, so as if that wasn't hard enough, take a look at hydrogen, or as I was going to subtitle it, how much trouble can you get from a proton? So if we're to look at hydrogen issues and burning hydrogen within a gas turbine, we've got a range of issues, I think, that come from temperature, cryogenic temperatures. If we're going to use liquid hydrogen, you've got hydrogen embrittlement effects, and you've got some sort of indirect effects of using hydrogen that then changes your atmosphere or your environment for the more conventional materials in there. So if we think through the system, at storage, we've got cryogenic temperatures, so we've got straight issues with cryogenic materials performance and embrittlement, whether they're non-metallics or metallics. Then we've got a distribution system with pipes and valves and control mechanisms and pumps, where we're going to have cryogenic issues, but we're also going to have sealing and joining challenges and issues with hydrogen charging and hydrogen embrittlement. We'll then be raising the temperature of the hydrogen as we go through the system to a temperature at which we can inject it for combustion. So we'll have, again, hydrogen embrittlement as we go through that kind of near ambient temperature range to consider. And then when we go into the fuel delivery system, we've got kind of go up to the front face of the combustion nozzle. We'll have potentially high temperatures from the flame, which will cause issues of hot hydrogen attack or hydrogen charging at elevated temperatures, as well as conventional material challenges. And then as you go to the kind of combustion and the turbine system that won't see any hydrogen because the hydrogen will have been burnt, we'll see issues with different flame temperatures, different flame velocities, different flame gradients, a requirement for different cooling arrangements and geometric arrangements that might bring in novel manufacturing techniques to achieve the new geometries. And we'll see a high water vapor content in the exhaust because the hydrogen will become water. So that's where we'll get these kind of environmental challenges that are not directly hydrogen, but they're indirectly associated with the combustion of hydrogen. So we need to understand all of those kind of issues and what they do to our suite of materials, from storage through pipework and pumps to the gas turbine, combustion turbine itself. And finally, we need to keep an eye on the sustainability of the materials we're using. As always, there's not that you can't have a sustainable product which is environmentally friendly in terms of its fuel consumption if it's not sustainable in terms of the materials we put into it. Materials can be critical or strategic in a number of ways, from expanding demand, limiting supply through global distribution or political economic issues, or there can be ethical and environmental issues associated with their supply chain and irregular unregulated mining or poor social practices or conflict issues. And we're familiar with that to a degree with nickel and platinum group metals and refractory metals, and we manage all of that. But the transition to electrical energy storage brings in those issues for a whole range of new materials, lithium for energy storage, cobalt again for magnetics, or rare earth elements for magnetics. And we need to be cognizant of that as we look back to our supply chain. Whoops. But I'd say, we know how to deal with that. We know what the tools are. Rhenium's a great example where we use it in turbine blades. It's a very potent strengthener, but it's a byproduct of copper and moly production. So it's relatively scarce and the supply doesn't react to demand particularly directly. So we needed to address that very, very robustly. And we did that through being really, really frugal in how we use rhenium in alloy design and in manufacture, capturing every last fraction of a gram through the manufacturing and all the foundry wastes and all the filter dusts and etchant wastes, and recycling to recapture all of our rhenium. So all of those tools of frugal materials design and application, squeezing the last benefit from every percentage that you add to your alloy, and then capturing all of it through manufacture and then recycling and closed looping, as well as establishing perhaps economic measures in the supply chain or financial measures, can all be brought to bear to handle these issues, but it needs to be done robustly. And that's it. Thanks for your attention. That's probably enough, and I'll happily take any questions.
Thank you, Neil. That was an excellent insight into some of the materials specifics, but the engineering more generally associated with what we're trying to do in the aerospace industries at the moment to meet the zero carbon targets, etc. A couple of people have already put questions into the chat. If anyone, now that the talk has been completed, if anyone has any further questions, please put them down in the chat and I'll ask those questions to Neil. So the first one from Robert Court. So some of these issues have been touched on already, Neil, but Robert's asking that he's heard that it's said that a car can consume as much energy during manufacture as they consume during service, up to 160,000 miles. Do you have any information? How does that compare to aero engines?
Yeah,
So,
I just skip back to this slide because that's kind of what this sort of chart addresses. So it's certainly true that there's a lot of embedded energy or embedded carbon by the time you've manufactured a large civil aero engine. So that embedded energy is not insubstantial. But it is true, and this, although schematic, is representative that the use is 99.9% of the emissions and environmental impact, because the aero engine will fly for 20 to 30 years, and it's flying for many hours a day through that entire time. They cover, potentially millions of miles, but the use phase is by far the most important. So that does give us a luxury, in a sense, that we're able to use difficult, expensive, or energy intensive elements and materials like rhenium in the system to give us a benefit in terms of energy efficiency or specific fuel consumption, and that then will give us a big overall payback. But it doesn't mean that manufacturing isn't important. And when you look at that manufacturing, most of the impact of the manufacture of the system is upstream of Rolls-Royce, which isn't surprising when you consider that its elements are dug out the ground and ores are refined and roasted, and there's extractive metallurgy and primary, secondary melting and conversion, and conversion to ingot and billet and forging, and then at the end, possibly within the domestic facilities, essentially we're doing some finished machining and surface processing and joining. So it's hardly surprising the majority is upstream. But no, it is true that for an aero engine, service dominates.
Throughout the talk, there's been lots of references to the automotive hybrid type systems. Has Rolls-Royce spoken directly to any automotive companies to ask them what were the lessons learned during their design manufacture?
We do, yeah. We have quite a lot of exchange with hybrid manufacturers in other sectors, I guess, internally and externally. Because we've got our own Rolls-Royce Power Systems doing hybrid systems for trains and heavy ground-based equipment, agricultural equipment, and quarrying and mining equipment, and so on, as well as the automotive manufacturers. So yeah, there's quite a lot to learn there, particularly perhaps from automotive when it comes to high rate manufacturing and automation. Yeah. Okay,
so going on to a second question from the audience. This time a slightly more sort of academic or technical question from Phil Irving. To what extent are there conflicts between mechanical or durability performance and electrical performance?
Yeah, I mean, there are clearly conflicts there. Many of the electrical materials, the active materials, are not optimized for structural applications. So you think of the magnet materials, neodymium iron boron or samarium cobalt magnets. They're ceramic-like in their mechanical behavior. They're sintered products. They're brittle. They damage easily. They're environmentally sensitive, so they need to be protected and supported by the rest of the system, mechanically and environmentally. And then the kind of resins and adhesives that are used in the creation of the lamination stack of the soft magnetics. You've got these 100, 200 micron thin sheets of iron cobalt that are all bonded together to make a highly dense, with the bond layers very, very thin, a few microns, a highly dense structure. But the glue layers between them are not. They're there. They serve an electrical isolation purpose, and they hold it together to assemble, but they're not particularly mechanically robust. So again, that needs to be considered. And then you've got all the kind of thermal issues of like the resins that are used in the impregnation of the coils and things as well. They're there to support the coils, and they're there to provide electrical insulation. But again, they're not mechanically necessarily all that robust, and they're not great thermal conductors. So there's lots of challenges between electrical insulation behavior or magnetic behavior and mechanical behavior. There's lots of complexity. And then, as I said, the imposition of mechanical loads on these things messes up their magnetic performance to a substantial degree.
And what sort of stage are you at with initiating that sort of laboratory research out in the universities, etc., at the moment?
We've we've done quite a lot of testing to support our demonstration projects and our early product development. It's tended to be sort of the pragmatically focused testing, so risk mitigation testing or validation testing. So we've done things that are based on demonstrating a performance environment for a given service life or duty. We're at the same time in parallel trying to kind of kick off the underpinning scientific research that then gives us that sort of broader envelope of learning. So we know that it's okay in this little regime for this service duty, but what does it do for much longer times at higher temperatures or higher stresses, and what's really going on within the microstructure that's giving that behavior? Those programs are just sort of, we've kicked off some work, and we're bidding for other programs in that area at the moment with academic sort of collaborators. Because as you'll know, Martin, we want to kind of understand these materials. I mean, you can never understand something completely, but we want to understand them to the same level we understand our other aerospace materials. And that's really not the case at the moment. You can kind of ask questions. Why is it done like this? Why is it processed like this? What's going on in the microstructure? And it's a bit like, well, kind of always been like that.
So you wouldn't say you've got a very comprehensive design database at this stage?
Not yet, no. No, not to the normal sort of standards of statistical basis that we have. I mean, we're generating the necessary data within the kind of regimes of design that we have, but we haven't yet sort of explored all the corners of that sort of design database by any means.
The Excel demonstrator program obviously was very successful in beating the present speed record, etc. Is there an obvious next stage demonstration or a next stage design that you're going to be working on to take some of these technologies further?
Yeah, so that was very much a demonstrator, I guess, of kind of what's possible. But we're using that and other demonstrators that we've done, and then the jumping off point for the products that we're now looking to bring to market. So there's a product for a sort of a commuter air commuter air vehicle, which is the kind of a sub-regional kind of market, and there's a product for the kind of urban air mobility market, to the sort of few-seater sort of helicopter replacement within city vehicle, which are the two kind of earliest to market products that we're working on now. But then there are others coming down the pipeline as well.
Yeah. Do you feel that we've got a lead in Europe compared to our US competitors in this area, or are we on a par?
It's hard to say. There's lots and lots of activity out there. There's lots of airframers active in this area, some established and some new starts. Some in the UK, some all around Europe, and others around the world. And there's quite a lot of potential power system providers as well active. I think we're well positioned. We have electrical expertise. We've got systems engineering expertise. We've got the electrical knowledge that we acquired with the former Siemens group that we acquired, and we've obviously got the understanding of the route to market as well. But then others are also active, so it's going to be a strongly competitive area. But I think that the knowledge of how to bring an aerospace product to market and certify it and validate it is going to be key.
And I think you openly admitted that the company's interest in hydrogen at the moment is still at the very earliest stages. But that sort of propulsion technology also needs some fairly dramatic changes in design for the airframe as well as the propulsion system. So presumably you do work closely with the likes of Airbus and Boeing.
Yeah, absolutely. So yeah, obviously the kind of fuel storage challenges are very different, whether it's cryogenic or gaseous. Yeah. And the differences in kind of gravimetric or volumetric efficiency versus kerosene and what that does to the airframe. So yeah, we work very closely with Airbus and going on those kind of concepts and what the whole system would look like. As we look at those kind of early demonstrators and technology demonstrators, it is early days, as you say, but it is progressing and will progress very quickly to component and subsystem level demos and then system level demos. Obviously, the hydrogen challenge is very different from another more kerosene-like drop-in sustainable aviation fuel. Should be, from a materials perspective, somewhat more straightforward.
Yeah. Okay, well, I think we've exhausted the questions in the chat. So if anyone wants to drop a very final question into the chat, they would have to be pretty quick now. Other than that, I think I'd like to thank Neil for a very interesting talk. Oh, I can see someone typing as we speak. You're not off the hook yet, Neil.
Going to be a good one. Oh, there we go.
This is a comment from Peter Rogers.
Thank you very much.
You and many thanks, and I'll sort of say that as well. Thank you, Neil, for a very interesting talk. A very fluid area of technology, and it's good to hear that the gas turbine isn't completely dead. And I think that is a serious point that a lot of the conferences I attended over the last 2 to 3 years, the engineers understand this, that the gas turbine has to continue to bridge that gap to these new electrical and hydrogen technologies. But we're going to be reliant on gas turbines for many years to come, and the politicians and the environmentalists need to understand that and work with the likes of yourselves to make sure that that's still funded in terms of critical research in that area as well.
Really important point that I'm always keen to make, that the hybrid system will still in many cases have a gas turbine in it, and the hybrid system, and the hydrogen system will be potentially a hydrogen gas turbine. So the gas turbine technology remains really critical.
That's right. Okay, so with that, thanks to everyone who dialed into today's webinar. We hope you found it interesting, and hopefully if you're not a member of the EIS, you may consider joining into the future. Please contact Sarah and the EIS office. Otherwise, with that, have a good afternoon, and hope to see some of you again on some future webinars. And thank you to Neil.
Thank you.
Thank you.